Simple. We'll start with simple. Simple linear regression is that there's going to be some line, some magical line called a regression line, called a trend line, regression line that minimizes the distance between the line and the points. It's often called a best fit line, regression line. Best fit because it's the line that minimizes the overall distance between the points and the line. So like for this group of data here that I put, pretty clearly something up here, something like this doesn't minimize the distance. The best fit line is the line that gets as close to essentially minimizing the distance between all the points in the line. I don't know if that's it, but something like that. It's easier to think about maybe if I do a tighter fit, where the points are see that right there? I need to regression technique, linear regression, finds the straight line, that's what's called linear, or the best fit line. It finds a straight line that minimizes the distance between the line and the points. That line has a slope associated with it. That slope is the predicted effect of x on y. And then it's got there's also some y-intercept there, whatever it is. So that line has some y-intercept, or whatever it is. It could be number 3. It could be y is equal to 3 plus 0.8 times x. That's your, if this is 3 here, this slope is a little less than 1, going up. But how did I get to that regression equation? The way I got to it was there was an actual set of data out there. And in this case, the x and y were tightly related. As x went up, y went up pretty tightly together. Regression technique finds the line that minimizes, that's not the distance, it's the squared distance, but the same idea, minimizes the distance between the line and the point. If the line were drawn down here, then each point would have much further distance from the line. So that clearly would not be the regression line. The regression line is the line that minimizes the distance between the sum of the points and the line. And that line then, whatever that line is, that line will have an intercept somewhere on the y-axis. The intercept's not usually the relevant part. The relevant part is the slope. The slope is the relevant part. And for each, if that's actually my equation based on that, for each 1 that x goes up, we would predict that y goes up by 0.8. For each 1 here that x goes up, y would go up by 0.8. One more amazing and basic regression concept, then we'll take it further. Here, maybe some of you have heard of r squared before. Maybe you haven't. But r squared, I'll write it down, r squared is the explained variation divided by the total, or it's the percent, r squared is the percent of the variation in y that is explained by a linear relationship to x. The percent of the variation in y, like the variation in income. What percent of the variation in income can you explain with the variation in, say, education levels?
Divided by what?
The total variation. And I'll show you in a second, sort of visually what that means. So here, just to give you 2 extreme examples for you, sort of most that are in the middle. If x and y look like that, and the points are like that, and the line sort of is just, could be anywhere, it ends up being somewhere. This would be probably 0% of the variation in y is explained to x. This x doesn't relate to y at all. It's just sort of random noise. It's random points anywhere. It's likely to be anywhere in the next one. That would be 0%. If the data between x and y actually go up like this, in a linear fashion, at some exact rate, 1 to 2, 1 to 1, whatever it is, that right there, if I could draw a line on top of the points, would be 100% r squared. 100% of the variation in y is explained by x. Those are the two extremes. The first one is, it's just random noise. You know, someone's education has no effect on their income. It's not the case, but if the data look like that, then if they look like just a cloud of noise, then that'll be 0% r squared. If they look like this, that's 100%. 100% of the variation in this y can be explained by this x. Every time x goes up by 1, y goes up by 1.2. That means that sort of x is the complete explainer of y.
R squared would be 1 or 100?
100%. 100% r squared. 100% of the variation in y can be explained by a linear relationship with this x variable. Most of the world's in between. Now let me show you how this works sort of for something like this. Let me take one random data point here. We'll take a better one. We'll take this random data point here. I'm going to take this random data point and explain to you how the r squared works for this one point. And the way it works for this one point, you add that up across all the points and you have the explained variation. Of all the y's here, of all those points here on the y-axis, somewhere in the middle, about here, perhaps, is going to be a y bar, an average of the y's. It just means it's sort of, it's just an average. So, you know, enough of the y below, enough of them above. That this is the average of the y's right there. That's y bar. That's the average of the y's. And I've got this from here, from the point, and from the point, which I should call it, it's one y, so I'll call it y hat. I'm going to call it anything right now. I'll just show you visually what it is. But from here up to here is the total variation in the y. From this point to here, that's the total variation in this one point. Total variation away from the average of y. At this point, at this x, at this education level, a high education level, at this relatively high education level, the line, the regression line predicts that it should be here. That regression line predicts that the person's income should be here. From here to here is something called the explained variation. That's called the explained variation. From here up to here is called the unexplained variation. Add the two together and you get the total variation. The total. So for this one point, 40% of the variation might be explained, 60% might be unexplained, and if all the other points were about the same as that, your r squared would be 40%. Of course, each point is different. And if you end up with data that looks like that, and you have your regression line, and then you have your average of the y somewhere about there. Notice in that case, for this one point, the total variation is from y bar, from the average of the y's, up to the point. But in that case, the straight line, the best fit line, explains most of the variation. This is the explained. The unexplained is just this tiny part up here. the unexplained is small. Add the unexplained to the explained, and you get the total variation. And so, in the case where the data are all can be fit closely together, that's where you get a high R squared, where the unexplained is small, the explained is large. And essentially, you can eyeball, before you even sort of like, with linear regression, simple linear regression, before you even crunch any numbers and such, if you eyeball something called a scatter plot, you can have a sense of, is this going to have a higher R squared? Is this going to have a 0.6, 0.7, 0.8, 67 or 80% of the variation is explained by this X? Or you can sort of eyeball data that